Okay, so good afternoon. Thank you so much for coming here. And you are going to be astonished at how different this is going to be, because I'm going to talk about social sciences and folklore, which is true, okay? The thing is, what could I say about, you know, big data and chemistry and physics and mechanical engineering? You'd all laugh at me. So I hope to be talking about big data in domains that would be kind of new to everyone, including to myself, and thereby introducing some concepts which are especially geared towards the students who are attending this presentation. This is a general presentation, and I'm going to talk just a little bit about the work that I'm doing with Munir, okay? So I'll start with a movie, which is not as interesting as the movie that we saw on molecular dynamics. It's a movie about big data in what New York City is calling its living laboratory. And this is what I hope it works. It should. Okay. So every internet minute, you have 6 million pages, you have 1.3 million videos are watched, 2 million search queries are submitted, whatever, gigabytes of global IP data are transferred, 6 new Wikipedia articles are published, 1,300 new people become mobile users, 100 plus new LinkedIn accounts are registered, 47,000 applications are downloaded, 61,000 hours of music are played, 20 million photos are viewed, okay, and 100,000 new tweets are posted. And New York, so, and there we go again, okay? Well, and
because it's every minute.
It's every minute. And thank you, thank you. This is a video I made of a page of a big data project of New York City municipality, in which all departments from health, transportation, education, construction are providing data daily so that they can start improving the conditions of the people who live there in all aspects. And what does this have to do with what CEPID, with our center? First of all, because there is a data infrastructure here, and I'm a data management person, but this is also about e-science, and e-science is data-centric, and it's discovery from data. So another way I could have called this presentation would be, how do I open this now? I am a computer scientist, but I don't know how to manipulate presentations. So, look, thank you. I need a chemist to do that. Thank you. The chemistry of computers and the mystery of buttons. Vonu what? Let's do a cooperative work as we usually, something disappeared here. So I do this. Okay. And, cadê? Onde? Vai você, eu sou míope, eu não enxergo nada. Tem view. Oh, thank you so much. Okay. So that's part of our cooperation. I bring the computer and will help me show things. The idea is the following. If we want to talk about data science, big data, e-science, we have to think about an evolutional paradigm in which up to 5, let us say 8 years ago, before these big data, data science terms were coined, the idea when you deal with data is that you ask, you know the patterns, and you want to find the data that match the patterns. So given the pattern, which are the data that satisfy this pattern. And in data science, which is a relatively new term, or in science, I know the data, and I want to find out the patterns the data fit. So we start in the past it was given a pattern, which data meet this pattern, and now is given the data, which patterns can I discover from these data? And so I'm going to talk a little bit about definitions, give examples of applications, and talk about challenges in computer science, but also challenges that we here at the CEPID are facing. And I'm not going to talk about this little soup of letters concerning technology involving big data. By the way, since I said I was going to talk about folklore and other things, I'm organizing a workshop in the beginning of September about big data, combining social sciences and humanities and environmental sciences. Because I think that in the future we should aggregate social scientists to a future CEPID, okay? But anyway, so let's start about definitions. So, the idea about this so-called big data is that it's data and it's big. So unless you understand your data and then you change the scale, you will not understand big data. The problem is that lots of people who talk about big data are overwhelmed by the volume and forget about the little details, which is why I like so much the pointillist example of the previous presentation. So what is e-science? Just to revisit, and why are we an e-science group? There are several definitions of e-science, but e-science is a joint research effort between computer scientists and scientists from other fields, so that we both, or all the fields involved, can provide and generate new science. There are contributions in computer science, in the CEPID, in chemistry, in physics, in bioinformatics, and mechanical engineering. And there are, at the same time, with our work together, we are developing new tools, techniques, models in computer science. So that is the idea about e-science. And e-science is very much related to data, where the part of cyber infrastructure sometimes concerns data, but most of the times concerns the physical infrastructure on top of which we would and we do work. And the idea within this e-science paradigm is that we follow the life cycle of data throughout scientific experiments. So the previous presentation was talking about data analysis. It showed lots of nice visualization results. And if I were to talk, which I will afterwards, to her, I would like to know, how do you store your data? Which models, which data models do you use to run your simulation? And how do you explain, understand, and trace back what you did so that other people can reuse your processes, your procedures, your simulations? And this is one of the areas in which reuse and traceability, in which I'm working with Munir and Lucas back there. Right, Lucas? Thank you for agreeing with me. So, so our idea is, this is my view of what we do in the CEPID. We are building, like Galileo used telescopes, we are building datascopes. Datascopes are instruments that let us look into data at different scales, like the presentation that we had. And there are hard problems such as capturing and storing the data, harder problems, which is from the data we get new insights and knowledge, and harder problems, which are some of the problems we face here, because we are a multilingual and a multi-speech and a multicultural and multidisciplinary group. And we are all putting our ideas and our data in our discussions. And for data scopes, as Erica just showed, we have to develop software as instruments to let us look into the data, analyze and interpret it. So if software is the instrument, what about data, and what is data? So data in our context is anything from experiments to models, simulations, papers, files, logs, and any kind of information that can be stored and which we can use to cooperate. Now, this is the idea behind our center, or one of the ideas behind, namely, I'm working in this part of the data sharing, data reuse of all data that is generated here. But what is big data? Now, big data is, there are lots of definitions for big data, and some of you may, how many of you have heard of the 3 V's? Oh, you have. What about the 4 V's? Oh, you have. What about the 6 V's? Oh my God, what about this? Oh, have you heard about the 100 million V's? Oh, good, okay, that's big data, big V's. Okay, so I have a 7V, okay? Well, maybe you've heard of the 7V. So the big data, the 3 first V's, which are the basic V's, are non-manageable because of the volume. Volume is relative, because things that were not manageable 5 years ago are very manageable today. But usually that means not manageable by traditional databases. Velocity is performance, variety is heterogeneity, veracity is quality. So these are problems, and all of these are open problems in computer science when handling data, okay? Then you have variability, because depending on the user and the context of use, you'll want other things. Visibility, because you want to see it in different ways. And the 7th V. Oh, do you know the 7th V? No, I was told about it last week, so, but maybe 7th V is value. Okay, so data is very valuable, and we have to be able to store it in a way that it can be reused. And as I mentioned in the slide before, a few slides before, data is not just static data. Data means anything that can help you reuse, rerun, reproduce, and verify your experiments in the context of this center. So, did you show this slide or not? Okay, this is an old slide from the beginning of our creation, prehistorical slide.
Genesis.
Genesis, yes, oh yeah. And the idea is that we are building a data sharing infrastructure so that different groups can take advantage of it, on top of which there will be algorithms, software modules, and so on and so forth. Another colleague of mine, is Guido going to give a presentation or not? But he's working and he's cooperating on domain-specific languages so that scientists can define their experiments in a way that they can be run more efficiently. And at the moment, I'm working together with my PhD student and Munir and some of other people here in how to store a record, a log, let us say, of your experiments via workflows so they can be rerun. The experiments can be rerun by anyone, and so that It's a kind of a live documentation. And one interesting thing, which is pleasing me a lot, is that my PhD student, which is a hardcore computer scientist, is reading lots of PhD theses in molecular dynamics in order to understand what he can do and what he cannot do. And we have meetings with the chemists. And the next step is that the chemists will have to read PhD theses in computer science. That's what the next step is going to be. I have another student who is here, Marcio, who's working on this training and dissemination feature on how to organize course material so it can be found and interlinked by different people so that courses given in mechanical engineering can be reused in the chemistry, molecular dynamics class. Okay, but that's not what I'm going to talk about. So I'm going to talk about data science. I talked about big data and the 7 V's. What about data science? Well, data science, I learned by preparing for a talk right before this one, but it was about data science, is that data science is the new buzzword, and if you want to earn lots of money, you have to say you're a data scientist, at least in computer science, right? Yeah, oh, good. So, I'm not a data scientist, but I'm learning to be one. So, as of 2 weeks ago, or 3 weeks ago, there were 219 data science graduate and undergraduate courses in the world. I mean, officially in the catalog of data science courses. And the idea behind data science is that you have big data and you analyze your data to extract patterns from the data. That is data science. Then you go to the different books and texts. This is a very interesting book for those who want to learn a little bit about the lives of people who at the same time teach mathematics in Stanford and work for the New York Times in helping them sell advertisement by using the same mining techniques they use in bioinformatics and in newspaper advertising. Okay, so this guy, one of the guys who's interviewed in this book, is a full professor at Stanford in bioinformatics and mathematics, who also is a full-time consultant for the New York Times on advertising. Okay? Another example, which I recommend for those who want to learn more about all the buzzwords in big science, is Hadoop for Dummies. It's really an interesting, easy to understand book, and I'm not ashamed of recommending for dummies books. Okay. Another interesting one is this data science and prediction of this journal in computer science of December 2014. And you find, little by little, if you look for the data science buzzword, you start finding all kinds of different things, even Wikipedia. So what is, oh, again, I'm citing Wikipedia. What terrible thing to do in a CEPID. But
most of the pieces are.
Most, but yeah. So these are some of the disciplines that, according to Wikipedia, concur to building knowledge in data science. And one very important one is statistics. According to this guy, who is one of the well-known evangelists of data science, you need to know math, you need to have expertise in some field, so you have to know your data, okay? You have to be a hacker. But anyways, machine learning, I don't know what the danger zone is because it's not explained, so you have to know about danger, maybe, I don't know. And data science is at the intersection of math, statistics, computing, and expertise in a given field. This is another view from Facebook. Statistics, physics, in your honor, and electrical engineering. Okay? And finally, you have thus that you have nerds at all the intersections, and you have awesome nerds, which are the data scientists. Okay, so this is another definition, which is the idea some people get. This is a business view, whereby you have data engineering to create your data sets. And then you have some sort of processes, automated processes to extract knowledge, which is what we are trying to do here, even though it's not really, as you said, we are still beginning to interact, right? Now, what can I tell you about data sources? One of the big data sources for data science is astronomy. Another, and astrophysics, right? Chemistry, I don't know. I have not seen many examples. I don't remember seeing any example. But that's something that has to be more exploited. But these are examples of what is data science is really used in the business world. So there is this thing called data brokers, of which there are 10 companies at least registered in the United States, that all they do is they go everywhere to grab people's data and create data sets and sell these data sets. And there was one firm, so these are the data, 700 billion data elements, 1.4, it's all the billions. Firm 2 and 3 firm, 3 billion new transaction records per month. So this business about big data and data science is really serious money, okay? Besides in astronomy and astrophysics, for instance, generating science. And this is a very good example of something which we would have to look at, and we should look at in our CEPID, which is making data public. So this is, the British are a very good example of open data for research. And they have very strong open data policies. And this is their site for social sciences data, which I found very interesting. We hold the United Kingdom's largest collection of digital but social data and social sciences. And one interesting thing about this site, which I recommend, is that it has mini courses on how to care for your data, how to babysit your data, change its diapers, kiss it goodnight, and sing to it, so that you'll have a healthy data set that will grow and become, right? Yeah, and become a living organism that other people can use. The second thing this is a very good site for is that it has lots of guidelines of how to plan your research, and including together with your research plan, how to create good habits in handling your data, which is something that we are trying to do here so that our processes and our data can be reused. Another example is the city of Chicago. Anybody here from Chicago? I don't, no, I don't think so. The city of Chicago publishes all of its data online, and every citizen is encouraged to use this data to build new tools to help the city progress. And you have over 700 data sets from crime occurrences, constructions, and one recent February but because I was talking to the guy who handles this portal, is a tool that lets you forecast where rats will appear. So based on 15 variables, okay? And then they can send the rat killers to this place, and the rats, that I don't know if the rats all of a sudden appear, but this is all based on doing simulations and eliciting information from data. Okay, and these are examples of the data sets. Now, some applications. I'm going to give you just 3 examples from the social sciences and medicine, because actually the social sciences are very, very, very big on data science. And the area of data science actually appeared based in social networks, Facebook and Google. So these are the great movers in industry, and thanks to them, social scientists are working in a new scale, because they are learning how to do statistics on top of on top of big data. So, application examples of data science, you can think of everything that requires you to apply statistical methods and simulation to big data. It has no, data science is about big data. One example, I'm still not at my 3 examples, okay? Computational social sciences is a new field that's based on graphs. So you create graphs with millions of nodes, billions of edges, and you do graph traversal. You look at the graphs in different scales, and you derive new relationships among humans, but you derive new economical situations, and you derive, as people do in the University of Northwestern University in Chicago, you derive information on how to build teams of scientists that can apply to NSF and succeed. So it's based on, built on network science, okay? The second one that I talked to you about is folkloristics. And this is one of my favorite examples about how you can start from a theoretically strange field, which is folkloristics, and you go on, design and develop new computing algorithms on top of folklore to discover correlations across stories, correlations across cultures that nobody knew about. So what does that have to do with us? We want to discover correlations from our data that we still did not know about. So 3 examples, 1 in Brazil and 2 in the US. The one from Brazil is something which is very vital to us, and which is, depending on how you look at it, is a good thing or a catastrophe, and which is we are diverting the São Francisco River, and I don't want to talk about it politically because I may be fired, but this is based, the simulation of the São Francisco River is based on a simulation of a graph of 620,000 nodes, and the entire Brazil can be seen on top of this graph, the hydric sources of Brazil. And it can be visualized at several scales, and all of the official Brazilian simulations on how to run our water sources are made on top of this graph. Now, what does this look like for the so this is Brazil's hydrographic network, and it's all blue because there are lots of little water courses all over. And if you go down the scale, you see lots of small waterways. This is where we are, São Paulo. And you can go up and down different scales, refining or condensing the graph. And this, if we move this to another field here, any of our research efforts within our center that uses graphs can reapply and reuse some of the techniques that are being used here on large graphs. Now, this is the San Francisco River. This is the state of Bahia. And this is the Northeast. San Francisco, I don't know if the Brazilians have seen this map yet, because I did not know it either. San Francisco is going to be diverted in these two ways, okay? And this is causing, so this is part of one of these ways that is being built. This is causing terrible ecological problems, but this is not my emphasis, okay? My emphasis is just to say, this is all graph-based algorithms, the hydrological simulations. And this is one of these two waterways that are being constructed. This is the normal course of San Francisco. Some of it will continue running like that, and the other two are being diverted. How to work with this? This is data science, this is big data, this is simulations on graphs. And this is from another scale. This is big data, but not really data science. Why? And I think that a lot of the things we do here cannot be considered data science because the algorithms used in data science do not apply to lots of the data we generate. So one of the nice opportunities of our CEPID is to do distinct kinds of data science from the data that we have. Data science does not believe in continuous variables, so anything that uses continuous phenomena is not good for data science. All the variables that, for instance, the hydrographic simulation uses, they are highly interdependent, like lots of our simulations here, lots of variables. Isn't that right? Yeah, you were the expert. Yeah, you're one of the experts. Highly interdependent, and the way data is organized is not amenable to data science simulations. So what would be data science examples? There's this question I need us to think about, and how we can progress along new algorithms on top of our data. So there is this New York, the quantified community, which I showed a video of, okay? And it creates 1 terabyte of raw information per day. And they are using this information to analyze the city of New York, which this is what they call living laboratory. So these are all statistics from their site that show how we are becoming progressively urban. Oh no, this is not. What do I do now? Okay. And the way buildings are evolving and getting old. And this is just saying that they are a unique public research center that uses New York City as its laboratory and classroom to help cities around the world become more productive, livable, equitable, and resilient. Okay? CUSP observes, analyzes, and models cities to optimize outcomes, prototypes, new solutions, formalize new tools and processes, and develop new expertise experts. Okay, so forget the first sentence, think about the second. CCES observes, analyzes, and models chemical phenomena, or mechanical engineering phenomena, or physics, or bioinformatics, to optimize outcomes, prototype new solutions, and so on and so forth. So how can we take advantage of things they are doing to New York City data to reuse it when applicable to our center? Oh my God, what's happening here? Okay, and finally, this was not the finally. So institutions that are paying for it, the whole city of New York and lots of companies. And finally, something that is very interesting, which is medicine and social networks. And there are two sites which I discovered recently. One is Patients Like Me. Patients Like Me has over 200,000 people that are registering their data into the site so they can build support chains and they can track their health. You can download software to see how healthy you are, and you can find other people with the same disease and you can exchange tips. And what I liked about this is donate your data for you, for others, for good. So this is give your data so that people can analyze the data to discover new things in medicine. The second site is this Foundation Medicine on Cancer, which is again based on donating data. And it has lots of data mining tools that let doctors find patients with similar diseases as the patient that you have. And then you either talk to that doctor and ask, what kind of disease, how did you treat it? Or you get insights on how to treat your patient. So now suppose we put our data and our simulations in our site, and other chemists or chemical engineers or chemists all over the world will look at what we did. That is the idea. And try to get insights and reuse, which is what we are doing with Munich. And finally, use of social networks in several fields. And this is the the team science research at Northwestern, which helps researchers find other researchers to build a team to create project proposals to be accepted at NSF. So based on statistics, profiles of people, personnel, it's really very interesting, okay? And this tool, this is data science. The set of tools is based on their analysis of teams that are successful, first at NSF, but also in winning games, internet games. So they analyzed a few million users of games and saw which teams, what is the team composition. You have to have a healer. You have to have a hero. You have to have, therefore, you have to have a priest. I don't know who's the priest here. And you have to have a warrior. And if you have these four profiles, you have more chance. So we are all heroes, but where's the priest? It's you. Okay, so the computational challenges, 5 minutes and I'll be done. First of all, we have to remember that we are moving from what data satisfy the pattern to what pattern satisfies the data. And this is the new way of working with data nowadays. There are problems in integration. There are problems in modeling. There are problems in visualization. There are problems in interpretation. There is the whole issue of a data life cycle from acquisition to interpretation. There is the problem, which is one of my research themes, about how to deal with heterogeneous data so that you can get meaning out of getting different sorts of data types together. and different types of scientists together. Privacy and security, which I don't think is a problem here, right? In the CEPID. We do not have, do we have private data here? No. But preservation and reuse is a problem.
Private in the sense that we don't share yet.
No, yeah, I mean, it's, just a second. It's, no, privacy, I mean, we are not dealing with diseases, even though we are now connecting with the hospital. So we'll need the privacy, we'll need to consider privacy issues about our data. But we do not have social network data. However, we need to worry about how to preserve for the future. That we need to do. Then there's a problem of reliability. And there are all the V's and the question that we need to collaborate. So I gave a few definitions on e-science, big data, data science. I mentioned some applications which are not the applications we are working with here. And a few challenges that are faced by the people who are working with these applications. And we are handling and dealing and coping with many, many data management challenges here at our center. Thank you. Oh, perguntas is Portuguese. It means questions. Okay, so thank you. I know there's coffee break. And is there a coffee break? There is no coffee break? Oh, okay. But thank you, yeah.
Any questions? I have one.
Yeah.
The most, for me, the most challenging problem in terms of thinking the things I do in the context of big data is going from this data that cannot be treated by conventional terms to things that need new techniques. I think I have never faced a problem like that.
Yes.
Maybe we have to think which. I think I don't understand exactly how could my problems become more interesting and more complex at the same time in order to reach a degree that big data analysis would be necessary.
Because,
this is a question, but we need to understand exactly at which point we need to start to use new techniques in order to analyze our data.
There are at least two answers to that. The first answer is that's because you don't have big data, okay? Which is a possibility. On the other hand, the whole idea of my presentation here was to waken people up to these definitions and make people, I mean, the CEPID group and so on, start thinking about, okay, we don't have big data because it's not trillions of whatever. Second, we do everything in an Excel spreadsheet or and that I carry in my pocket or even in a piece of paper. I don't want to exaggerate, of course, but or I deal with time series. Okay, so which is something that occurs frequently when I talk to people here. So what kinds of and that's the second answer. What kinds of new discoveries can be made in computer science that will help you design new tools, develop new results, have new insights from your data? How can I help you better explore your data?
And maybe something that we need is to understand which are the tools in computer science that are being used. So if we understand a little bit more about the tools, we could reformulate our problems in view of the possibility of using the tools that we don't know that those tools exist actually. The tools and algorithms and models and vice versa. Okay, so Lucas is working with workflows for traceability of experiments and reusability, right?
Because we were talking about that on Friday, and you said, oh, our original idea was what?
What about we use data in the models, and now we are trying to the traceability of the logging, navigating the logging of this kind.
Okay, so his original, he says, how am I going to write a report if my thesis was 100% changed? Okay? No, well, 99%. So the question is, we had this original idea of working together. By working together, the Munir's group changed some of the things they thought they knew and had new insights. And we had new insights about how we could better reuse or adapt or create new tools to help traceability, to help understand provenance, to help quality. So that's what we really need is to talk.
I was going to add one thing. Certainly the volume, our data volume, is not one of these.
Trillions, no, it's not.
It's not. But data management in the sense of reproducibility, archiving, workflows to generate, let's say, a set of simulations without having to do all by hand. Those are two aspects, for instance, which is very important. How do we keep our data? How do we store our data? We want to be able that if somebody wants to reproduce our calculations, they can reproduce our calculations without having to read, the little underlying things, the hidden things that it's inside the methods. What are exactly the residues which are protonated and which are not protonated? Oh, this guy did that or did not do that. Sometimes, very often, we try to reproduce calculations and we failed. Quite often we are doing something wrong, or the person trying to reproduce is doing something wrong, or there is really something wrong with the original data. We've faced this situation before. So it's very important that I think the agencies, and FAPESP is very keen into that, the agencies in general are more and more so asking for the description of how you treat your data, how you store your data, how can you retrieve your data, and not not just for reusing, but also for accountability.
Mm-hmm.
So this in the center, for instance, is very important for us. Not that we do simulations; it's easy. We can put everything in one file and say, "You run this, you're going to get everything else back." But there are instances, for instance, in biology or bioinformatics, that this may not be so. So
yeah,
we hope to be able to contribute.
That's what we are doing with Lucas. I just, as you were talking, I remember something which is very interesting. Elsevier, I don't know if you are aware of that, has now some journals which are called executable journals. One of them is on computers and graphics. An executable journal, I think this is the first slide, I'm not, just a second. Okay, so this is from a talk I gave to librarians last year. So, oops, what is happening? Oh no, where's the executable journal? It disappeared. Oh, there you are. Okay, an executable journal, each paper is edited using this tool called collage, and papers are executable, and you can enter a paper and change the parameters, and you can execute new simulations with the paper's data, and you can do it online. So you provide, and this is something, okay, that we are not aiming to publish executable papers, let us say, but this is reality. You store your data, you store your experiments, you store your parameters, and you can go to a paper and run part of its code. So this is the actual figure provided by the simulation and computer graphics. And that is a figure I generated changing parameters in the code published online in Elsevier's paper. Okay? So just imagine reusability and traceability. This goes back to the paper's author. This raises lots of other issues of who's the paper's author, okay? Because if you change the simulation, you can publish a new paper based on that paper, and then, you know, what happens? This,
That's good, right?
that sure is good. Well, I mean, yeah, but, so, I know, there are all these problems associated with it.
I mean, today we use a lot of open source code.
Yes.
That if we had to write our own visualization code and our own.
Yeah, but now suppose that, which is one of the ideas that we have had similar tools available here in our center, so other people can go to our, well, get our data, rerun the experiments, and change the parameters. You should, or you, I'm not saying you should, but if you're interested in that, just go to Elsevier's and look at executable papers, okay? And you can run molecular dynamics, in the future, molecular dynamics experiments, changing parameters and obtaining bizarre stuff, because unless you know molecular dynamics, but this is just an example of things that we might achieve. Not necessarily big data, okay? I just use big data and data science as definitions and motivation. Not that we do big data here. I don't think we do, okay? Sorry, this was not in the script, but it is. Oh, it is not.
I wanted to see transparency number 5.
Oh. What was transparent? Well, you are joking, right?
I'm joking.
Oh, okay.
But I do have a serious question.
Yeah.
There are hundreds of scientists, thousands of scientists doing molecular dynamic simulations on many different proteins, or many other different systems. You run the trajectories, and you know, you take together this trajectory may not be your big data, but to us is big data, because it's expensive to generate, and it's a lot of data. And then we do an analysis on these trajectories, and we analyze certain aspects of the trajectories, and then we extract the information we want, we plot some graphics, some analysis, and we leave the simulations in some hard disk somewhere in the corner of the room. And most people do this. It would be really nice if somebody could revisit the simulations and perform different analysis on the same trajectories. Isn't something useful? I'm asking actually for the meeting. Or people rather run their own simulations again, repeat other people's, reproduce other. So I'm asking is, if we had a bank of trajectories with, you know, all the right and the proper care
And documentation,
that, you know, it has to be done like this, and all the, I mean, it's not junk trajectories there, it's good trajectories.
There is one case of that, you know, the David Shaw at his company, he has simulated, I don't know how many microsecond simulations of the folding of a protein, a reversible folding of a protein, and he has disponibilized the whole microsecond simulation for other people to analyze it.
So, but that's very interesting. But let's say now someone has, I don't know, Jim's simulation, 500 nanosecond simulations on, I don't know, lipase A. Oh, I'm also interested in this because I have lipase B, and I want to compare lipase A with lipase B, but I don't want to have to simulate lipase A anymore. So, I'm not sure if this is useful.
We've done. I was involved in a program in the UK about 4 or 5 years ago, called Bauzer, which was to do exactly what you described. It's a very interesting project. We had a big e-science initiative in the UK about 7 or 8 years ago.
Yes.
We ran for about 5 years. We had all the projects, and it was precisely, exactly about what you just described. And it was a very interesting project, actually. I'll be honest with you, in the end, it was not a success. But we learned, as is often, you learn more by your failures than you learn by sometimes by the things that worked. But what was interesting was that, yes, why didn't it work? And there were some reasons for it. One was actually that you have to have trust in other people's data. And I think what we discovered was that actually, although we believed that we were all part of one big community and that the people that we were collaborating with were our friends, when it actually came down to do we actually trust the data, it was, well, I don't exactly know how they did that really, and I think for security, maybe I'll just do it again.
Yes.
So that was one of the reasons. Another reason actually was just technological. We worked with a group of computer scientists who produced this amazing framework within which we could all deposit our data. But we discovered that in fact, although it was incredibly robust, it was distributed, it had fantastic SQL queries for anything we wanted. You could retrieve a trajectory at the rate of about 1 frame per second. It was actually practically unusable. And that was a communication failure between the domain scientists and the computer scientists about what actually they needed from the technology. So what we learned there actually was that it's really, really important to have excellent communication between your computer scientists and your domain scientists. And what was interesting is that we, to some extent, failed, even though technically we had those people working almost next to each other. I think the thing is saying just because people work next to each other doesn't mean to say they necessarily pay attention to what the other person is doing. But then the other thing that we discovered, which was also, I think, something that all these problems could be solved. The other problem is that the great technology that was developed in order to help us share our trajectories and do all this analysis required people to change their way of working.
Yes.
And people don't want to do that.
Yes.
So, I mean, I strongly encourage trying this again, because in fact we're going to try it again in the UK as well. I think you learn from these things though. But there are problems, but I would say they're all addressable. But yeah, you learn by experience.
What about, because for instance, this is really very interesting. There are lots of stories of failure in several sciences, for instance, biological sciences, because computer scientists insist on building databases and biologists want to produce spreadsheets. Okay? So what about whatever is it you guys use in trajectories? If the computer scientists had simulated that you were doing whatever it is that you usually do, instead of creating a complete new way of working, that would have worked. Yeah, I mean, that might have worked.
That might have worked. I think that was exactly the sort of thing. There's another approach actually, is that in some ways you say, I'm just going to forget about the people who have been working in this field for 10 years, because I'm never going to change the way they work. What I'm going to do is I'm going to concentrate on the new graduate students and people like that, the next generation. Let's make the new generation work in a new way. And for the current people, well, bad luck.
Thank you. Yeah. But
there's one other aspect. I don't know if we need to cover up, but there's one more aspect, is that perhaps the price that you pay today to run certain simulations, in 5 years, it's going to be like nothing. So that is also a very important point, because the computers get faster and faster and faster, or the codes get faster, and so what today may take, a certain simulation may take 3 months. 5 years from now, it's 1 week work.
Yeah.
There's also the question, sorry, again, another issue about the value of the data.
Yeah.
As we all know, if you could take exactly the same input parameters, exactly the same starting structure, the same code, but if you run it on 12 cores instead of 6 cores, you'll get a different trajectory.
Yes.
So what actually is the data that matters? What is it that you should keep?
Yes.
should you have the input files that allow you to reproduce it? Or is it the output data that's important? Or is it something that you extract from the output data which you believe should be invariant to these essentially immaterial changes? And again, some really interesting conversations to have there about what actually is of value for what you do in your science.
Okay. Thank you very much again, Claudia.
No,
We are
thank
going
So now let's go out and kill the old